Okay, so hello everyone. Welcome to the second last lecture, I think, of the course. We ended the discussion last week on an interesting note because we had discussed the issue of state-dependent operators. And so let me just remind you what those state-dependent operators were. I mentioned last week that if you use these state-dependent operators, one could use them to find a resolution to all the paradoxes that we found for large black holes. I'll just try and demonstrate that in the first part of this lecture. And then in the second part, I'd like to go on and discuss some puzzles that state dependence itself leads to and the extent to which those puzzles can be resolved. Let me remind you very quickly of what we said last time. So what we said last time was, if you have some black hole microstate, let's call it psi, then it is possible to find these operators, which we called mirror operators, which have the right correlators with operators outside the horizon. For instance, if you looked at the mirror of a simple annihilation operator at a frequency omega, then the mirror of that was, just one second. So the mirror of that was defined to satisfy this kind of an equation. And so you see that within what we were calling the little Hilbert space, this A here was a simple operator, was what we called a simple operator, which we discussed at length last time. And so within what we call the little Hilbert space, which was the span of the set of all simple operators acting on the state psi, you see that this A tilde acts exactly like an ordinary operator. So it acts like a linear operator. It satisfies some linear equations. In fact, it's defined via those linear equations. So it acts like an ordinary operator, and it also gives us the right correlators that we expect from effective field theory. And the point of state dependence, though, was that if you took some other operator or some other microstate, which you call psi prime, which was not related in some simple way to this microstate psi, then you could define also for that a mirror operator that had this property. And the point of state dependence was that these two operators, the ones you define here and the ones you define here, may not be the same operator because they're acting on different states. So if you have an infalling observer who falls into a black hole when the black hole is in the microstate psi, that infalling observer observes the operators which are A tilde omega. If you have an infalling observer who falls into the black hole when the microstate is psi prime, that observer naturally uses a different set of operators, which are these A tilde omega defined around psi prime. And these two may not be the same. So even though in a sense, we're asking the same question in both cases, in that we're asking, what are the operators that the infalling observer interacts with behind the horizon? We are saying that, those operators may be different depending on the microstate of the theory. Okay? So this is certainly a somewhat unusual idea, and we'll come to discuss some of the consistency conditions that one can place in this idea. But before I do that, I just want to follow this idea and show you how it resolves all the paradoxes that we previously found for black holes. So this is an important thing. It's the fact that if you use state dependence, it resolves really all the paradoxes for large ADS black holes. And also for the eternal black hole. So as I said, we'll come to the consistency of this towards the later part of this lecture. But first, I just want to demonstrate the statement that I have written right now on the slide. Okay. So let me remind you of some of the paradoxes. In fact, the reason it resolves all of these paradoxes should be clear from those of you who remember how these paradoxes were framed. If you go back and you think about how these paradoxes for large ADS black holes and for the eternal black hole were framed, you will see that they were in each case, they were framed by saying that, here we have some operators, and now let's do a trace over the Hilbert space. And then let's use some properties of the trace and then show that, this operator that we have is not consistent with various other global constraints that one might get from quantum mechanics. But whenever one does a trace over the Hilbert space, one is tacitly assuming that the operator that you're summing over is not changing in the trace. Right? If the operator is different for different microstates, then it doesn't make sense to do a trace. You can ask a question about, what is the correlator within a certain microstate, but it doesn't make sense to do a trace. And we will see that that is what resolves all of these paradoxes. So the common element to all the paradoxes that we explored, I think now 2 or 3 lectures ago, was that each of them involved a trace, and that is why state dependence is able to resolve all of these paradoxes. So let me just show that to you in a little bit of detail, and then I'll discuss the eternal black hole also, because that also gives some insights, I think, into the origins of state dependence. So let me remind you that there was what we call the negative occupancy paradox. The negative occupancy paradox was the statement that, because we had these operators which had the wrong commutator with the Hamiltonian, it didn't make sense for them to have the right thermal occupancy in a typical state. But you can see that if you just compute the expectation of the mirror operators about a typical microstate, so this psi here is a typical microstate, then you just go through the rules and you will find that this looks like into an e to the beta omega by 2, and you apply the rule once more and you will find that this becomes, and the e to the beta omega by 2 factors cancel out. And this, of course, is 1 by 1 minus e to the minus beta omega. So you see that it is indeed the case that the mirror operators have the correct thermal occupancy in a typical microstate if you define them the way we have defined them. Okay? And you just see that by applying the rules. First, you turn the a tilde omega into the a tilde omega dagger into an a omega, and then you use the rule for a tilde omega, and you will find that you get the right answer here. However, what does not work is that if you try and evaluate trace of e to the minus beta h a tilde omega dagger, this trace is a subtle thing to define. Okay? So let us say I define the trace as a sum over energy eigenstate. So an energy eigenstate, as I said, is something in which you can define the mirror operators. So let's say I define the mirror operators in an energy eigenstate, and then I try and evaluate this occupancy. So I can define the trace this way. Now, the trace for a state-dependent operator is not well defined, but let's say I define it by this equation. Then that's fine. I can evaluate that trace. In fact, if I evaluate that, I will find this answer, because in each typical energy eigenstate, this occupancy will come out to be this. However, if you do that, this is not equal to, the sum. You can't use the cyclicity of the trace and move this here. So if you now say, oh, by the way, I can move the mirror operator to the left because I can move the adjoint here, the adjoint of the creation operator to the left, which is what we did for the trace. If this had really been a trace, then in the trace it is indeed true. And if this had been a state independent operator, then it is indeed the case that for state independent operators using the cyclicity of the trace, you can move this a dagger to this side. But you see that for state dependent operators, it is not the case that you can move this a dagger here. And the reason is that this a dagger depends on the microstate. And so the cyclicity of the trace that you use, does not work. And you cannot, this identity fails. So the identity of going from here to here fails. And you can easily check that once that fails, there is no more paradox anymore. So you can evaluate this expression, you can evaluate the sum, and you will find the correct answer. And it just so happens that this expression is not equal to this expression, because in taking the trace, you tacitly assume that the operator was the same in every microstate. I want to emphasize.
Hi, Suvrat. So is it clear that it's basis independent, the trace of a tilde dagger?
No. So the trace is not a well-defined quantity for the state-dependent operator. It is not basis independent either, as we will see next time, as we will see in 2 minutes. So, all of these properties of the trace, such as the fact that it's basis independent, or the fact that it's cyclicity, they all assume that, you have, they all make sense for state independent operators. When you have state dependent operators where, this might vary from one energy eigenstate to the other energy eigenstate, it doesn't make sense to take a trace. And we will in fact see the lack of, that's why I said that, defining the trace is something subtle, but I just chose to define it as this sum over energy eigenstates. Okay? And if you choose to define it this way, then it's still not true that this sum is equal to this sum.
Okay, thanks.
So the point is that the trace, the reason this is a resolution that makes physical sense is that the trace is never directly physically observable. Right? The trace is not an observable. There is no infalling observer who observes the trace. The infalling observer, falls into a certain microstate, and in that microstate, the infalling observer observes some operators. But the infalling observer does not observe, does not have the power to compute a trace over all of these experiences. The trace is a convenient mathematical thing to do. But if you ask about what the trace is doing physically, what the trace is doing is, you're computing the experience of the infalling observer in all of these microstates, and then you're averaging over that experience. And of course, an observer in a single microstate can't do that. If you have some super observer on the boundary, that observer, can take a trace or can ask, first I prepare it in one state and then the second state and then I average over all of these. But the trace is not directly a physical observable. And therefore, it makes sense from the point of view we have been taking, where we're asking about an observer who's falling in a particular microstate, that, it might not be the case that the trace obeys these properties. And even though this is a sign of the fact that this is state dependent, if the observer could see this, could in some way measure this trace, the observer would see that the operators the observer was using were not standard operators. But the point is that this trace is not something that is directly observable. Okay. So the same resolution works for the other paradoxes we had as well. Let me remind you about another paradox. Remember, we had this paradox with this infalling number operator.
Excuse me, can I ask a question before?
Yeah, sure. Yeah.
I just wanted to ask you once more why, I think I didn't understand why the cyclicity of the trace doesn't work.
Sure. So you see, if you just take this expression, it's not true, of course, it's not even true if this was an ordinary operator that term by term, these things are the same, right? So term by term, these things are not the same. That's not even true for an ordinary operator. But it is true that for an ordinary operator, because you're really taking the product, you're taking the trace of A, B, and you're taking the product of two matrix elements. It is true that you can move things around. But when you have state dependent operators, it's just manifestly not, it's manifestly true that the cyclicity fails. In particular, you can evaluate both of these expressions. This expression here looks like E, e to the minus beta E. Let me just, so this looks like e to the minus beta E, and then looks like 1 by 1 minus e to the minus beta omega. Whereas this expression looks different. So, you'll pick up some factor of, let's see, e to the minus beta h. Let me add a factor of e to the beta h. So I hope I don't get this wrong in real time, but right. So this is e to the minus beta omega, and then you will get so you'll get a factor of e to the minus beta omega from here. You'll get a factor of e to the minus beta e. I'm just evaluating both expressions for you. And then you will get something which looks like a omega tilde a omega, which is e to the minus beta omega, I think, by 1 minus e to the minus beta omega. So, you just explicitly see that these two things are not the same. You'll have some sum over e to the minus beta e in both cases, and you sum that over e, and once you divide by the partition function, which actually I have not divided, I should have divided. Once you divide by the partition function, then this factor of 1 by on top will just give you 1, this sum. But apart from that, you have this constant term which just doesn't care about the energy eigenstate you're in. I mean, provided you're at a certain temperature. And here you have a different expression. You have something which has like these factors of e to the minus beta omega. So it's just manifestly not true that the trace is the same. And the reason for that is that when you use the cyclicity, you're assuming that it's the same operator that's acting on all the elements of the basis. If this operator a tilde omega starts varying with different elements of the basis, then it doesn't make sense to take a trace. You can see that also with the entanglement entropy and with other with other situations. If you have some operator where the operator itself is varying with what element of the basis you're having, then the cyclicity will not work.
Perfect. Thank you very much.
Yeah. So I have a question about this.
Yeah.
The concept of the cyclicity does not hold when the operators are state dependent.
Sorry, can you say once again, please? There's some disturbance.
Sorry. We have a conclusion that the cyclicity does not hold if the operators are state dependent, right?
Yeah.
So, but it assumes some kind of definition for trace, right? Because it's
So I chose a definition for the trace. I picked a definition for the trace.
but it's a usual definition. I mean, they normally we use.
Sure, but I mean, this is how we got the paradox, right? We got the paradox by doing this. So, there is the point is that whatever definition we explicitly finding that you take this trace, you take this expression, and you find something which is 1 by 1 minus e to the minus beta omega because of the way we define these operators, right? That just tells you that so now I'm just trying to trace back, and earlier we had a paradox saying that you couldn't have gotten this answer. And I'm just trying to trace where that paradox, where the argument fails, and it fails here. So any argument you construct that says you can't get this answer will fail because you explicitly, the operators are designed to give you this answer. So I'm just pointing out why the previous argument failed. If you construct some other definition of the trace, it'll still not be true that the trace is cyclic, as you can see, because if the trace had been cyclic, as we showed in this paradox, you would have got the wrong answer.
Okay, yeah.
I mean, you can take this as a proof, if you like, that no definition of the trace can be cyclic. Here, I've given you one example, but the demonstration that you get the right answer in typical microstates, you can take as a proof of the fact that for these state-dependent operators, for no definition of the trace will you get cyclicity. It'll never be the case that trace of this is equal to trace with the dagger moved here, as you can see in this example.
I mean, state-dependent operators are just not linear operators. So you just can't use standard properties from linear algebra anymore.
Correct. That's right. So they're linear within this little Hilbert space, but beyond that they're not linear, and therefore you just can't use these properties. Exactly correct.
I have a question. Like, so can I bend it to say that an infalling observer can never experimentally verify ETH or something? Say
Can never what?
energy. Say
you
like
can never experimentally verify ETH. For sure, you can't verify ETH, right? Because if you want to verify ETH, you want to look at typical energy eigenstates. I mean, how can one infalling observer verify the ETH? You can assume that the theory obeys the ETH, but how can one infalling observer verify ETH? But I don't see how that's relevant to the question of state dependence. Actually, how is
no,
that?
I was thinking like this our definition of trace is like a expectation of thermal ensemble or something, right? I thought right. If you ever want to fall into energy eigenstate and right. then and try to compare it with some thermal expectation, you're kind of saying that is not a well-defined comparison.
No, that's not actually what I said. In fact, if you define this to be the thermal expectation, you will get the same value that you have here. So if you look at this and this, if you define the thermal expectation in the way I've defined it here, you will get the same value that you have here. This trace of e to the minus beta h is just not a well-defined thing. If you define it to be what you have on the right-hand side, you will get this. So, you will get the right answer that you expect if you're falling into a black hole at a certain temperature. I'm just saying you're not allowed to do some abstract manipulations with the trace, which you did to get the paradox.
But doesn't the cyclicity also physically mean something like
no,
some
what
crossing
does
or something?
Mean physically? No,
I would have thought it's some crossing or something. Okay.
No, the cyclicity of the trace is something which you can which doesn't have any direct physical meaning. It's a statement which is true, but if you're an observer in a given microstate, you can't verify the cyclicity of the trace. The cyclicity of the trace is comes from the fact the cyclicity of the trace is never true term by term. It comes from the fact that if you had a linear operator, you had the state independent operator, you would have you would have some differences in every term, but the differences would cancel out because of some global property. But the cyclicity of the trace is just not it's just not something you can verify directly.
Thanks.
Okay, so we can ask now a question about the same kind of question about the infalling number operator. So let me remind you, we had this infalling number operator, which looked like this. And there was a second term, which I won't write to save time. I'll just write it as a dot, dot, dot. There's a second term which looks very, very similar. But if you look at this infalling number operator, you see that NA on a typical state is just 0. And it's 0 because A omega tilde dagger on a state just happens to be A omega with in e to the beta omega by 2. And if you just plug that definition in, you see that this operator just annihilates the state. And that tells you that, as you would expect, you do indeed find that the expectation value of the infalling number operator is 0. On the other hand, it is also true that if you were to evaluate the, so this is in a typical state. If one considers a state which is a state that satisfies, that's an eigenstate of the Schwarzschild number operator, such a state is not a typical state. It's not a typical state because it in fact violates one of the conditions that we used to set up the mirror operators, because this state is annihilated by a simple operator. So this state is not a typical state. And you could try and do the mirror operator construction in the state, but it would not be surprising. I mean, the mirror operator construction, as I explained, would fail. But let's say you generalize the mirror operator, it would fail because, you know, the mirror operator construction used the fact that no simple operator annihilates the state, whereas here you see n omega, which is a simple operator, minus n times the identity acting on n annihilates the state. But if you were to generalize the mirror operator construction and you were to find, and as you do expect to find, that the infalling number operator is not 0 in this state n, this would not be a contradiction, because it would not be the case, as we discussed previously, that the sum in energy eigenstates is equal to the sum in number eigenstates. And that's again because these operators are state dependent. And so the sum over energy eigenstates of this infalling number operator would not be the same as the sum over these energy over these number eigenstates of the same infalling number operator. And if you remember, this is what it was, the equality of these sums that was used to set up the paradox. Because the paradox was that, look, if you evaluate the term in this basis, then you get something that's non-zero. Whereas if you evaluate in the left basis, you expect to get 0. And that was the paradox. And here you see that, you know, it's just not the case that these two are equal, because this operator in the middle is state dependent. And so, as we discussed, the trace, which is what you're doing here, doesn't have an invariant meaning. It doesn't have a good meaning. You could decide to define the trace as a sum in energy eigenstates, or you could define the trace in this way, and it would just have different meanings. The fact that the trace is basis independent is something that holds for state independent operators, but it does not hold for these state dependent operators. Okay. So you see that this paradox once again involves the trace, and if you allow this operator NA to behave differently in an energy eigenstate and differently in a number eigenstate, then you would not run into the kind of paradox that we ran into earlier. This is the same with other paradoxes. There were other paradoxes that were constructed for large black holes, but a uniform property of each of these paradoxes is that they all involve the trace. And if you have state-dependent operators, the usual properties of the trace, such as the fact that it's basis independent or such as the fact that it's cyclic, do not hold. This is not something that's directly physically observable because you don't observe the trace. So the trace is, you know, saying you sum over some set of microstates which are all very different from each other. And if you drop the assumption that the operator is the same for all of these microstates, then it would not be the case that, you know, the trace has these usual properties. And that's what allows you to resolve these paradoxes. Let me now turn to the eternal black hole, because I think things are interesting there, and it also tells you why you need state dependence. So let me remind you that we had this paradox for the eternal black hole, and the paradox was that one could not find a set of operators that behaved correctly in this thermophile double state, which I remind you looked like this. So we had this thermophile double state, which looks like this, and we could not find, there is no single operator that works correctly both in the thermofield double state and in the time evolved thermofield double state. Okay. So this was the paradox that we set up equal to factor of 2. Okay. So this was the paradox that we set up. We said, look, if you want an operator that works correctly in the thermofield double state and in the time evolved states, there is no such operator. You can go back and look at the paradox, but it follows quite simply, once again, from the kind of paradoxes we set up for the single-sided black hole. And of course, there is one thing you could do, which is you could just take the thermofield double state and you could define the small algebra about the thermofield double state, define a little Hilbert space, and you would get some mirror operators that would work correctly. And you could do the same for each of these states as well. But I want to describe a slightly different approach to understanding these mirror operators, which is very useful in understanding why it is that state dependence arises. So in general, I think this issue of state dependence is best addressed in this eternal black hole because it really crystallizes the issue and makes it quite simple to understand. Okay? So in fact, when we were discussing this eternal black hole, there was some discussion about, aren't the mirror operators the operators from the left CFT? And we can now return to that discussion. And let me point out that, it is indeed very tempting to use the operators from the left CFT as the mirror operators, because the operators from the left CFT do satisfy this very nice property in that they have the right correlators with the ordinary operators. And the correlators that they have, you can check in the thermofield double state, are indeed all of precisely the right kind that you need. And of course, they also have the right correlators with themselves, and they commute with the ordinary operators. So you would have said, well, these are the right operators, these are the mirror operators. So what is wrong with them? What is wrong with them is that if you look at the time evolved states, which are these states, then you would expect that in these states as well, the correlator should be unchanged. It should be unchanged because, whether the correlator has the right value or not tells you whether the state has a smooth horizon or not. And these kinds of states are just, something where you've acted with a large diffeomorphism on the eternal black hole geometry. Ultimately, these states, tell you the experience of an infalling observer who falls in after a time t. And it should not be the case that an infalling observer who falls in at a later time encounters a firewall, whereas an infalling observer at time 0 and does not encounter a firewall. That would not make any sense because there's no origin of time. And so, this correlator should also have the same value as the previous correlator. But if you evaluate this correlator, you see that this term here, this HR acts on this A omega. This is a right operator, A omega. This is a left operator, so it evolves under this HL. And in fact, the phases don't cancel. They don't cancel because both of these are annihilation operators. And so the phases add up, and in fact, you get this answer. And this is just wrong, because if you really were to have this answer, it would tell you that in the eternal black hole, you develop a firewall after a short amount of time. At time 0, the eternal black hole is smooth. But if you were really to say that these A omega L's are the correct operators, then they would tell you that, you time evolves the eternal black hole a little bit, and you end up with a firewall. You end up with a firewall because you now have this phase factor. And this phase factor is not allowed. It tells you that the operators inside and the operators outside don't have the right correlator, rather they've got dephased. And this phase factor would tell you that there's a problem with the eternal black hole geometry. So it tells you that, A omega L can't quite be the right operators because of this problem that, they don't behave correctly in the time shifted states. But you can fix these A omega L operators. So we can improve A omega L to get A tilde omega. And let me just explain how that happens. You see, we could define, let's define a projector onto the little Hilbert space of that's constructed about one of these time shifted states. So let's define this projector, which we'll call PT, which has the property that if you act on one of these little Hilbert spaces, it gives you back the state. Okay. And PT on psi on some other x is equal to 0 if x is not an element of the little Hilbert space constructed around psi t. So I hope this definition of PT is clear. In fact, in the lecture notes as they're currently on the archive, there's an error because PT is just written as psi t, but that's not correct. It should actually be the projector onto the full little Hilbert space, not just the projector onto the base state. So I'll fix that. But for now, I hope what's being explained here is clear. In that PT is the projector onto the little Hilbert space as constructed about the time-shifted thermofield double state. So that's all I have written in these equations. Okay, so PT is a projector. It projects onto one of these little Hilbert spaces, and it's a function of t. So PT for a different t projects onto a different state. Okay, so PT is a standard projector. And now we could do the following. We could say, let me write down the following operator. So there are some prefactors.
Sorry, in your previous, in the last line, this is 0 if x is not. Yeah. Okay.
Yes, x is not. Thank you. Thank you. Okay. So let's write down the following operator, which is, it is now a omega L, but I have added an explicit factor of e to the I omega tau. And now I have this p tau, which is the same p, except that, I write it as tau because I'm integrating over d tau. And I'm doing this over some long period or from some cutoff from minus theta cut to theta cut. We'll return to these cutoffs in a minute. But for now, here's an integral. This C happens to be the specific heat. But this normalization is just some normalization. This beta is the inverse temperature. And apart from that, we have the left operator, except we have multiplied it with e to the I omega tau and p tau and done an integral. Okay. So why does this operator work? The reason this operator works is, this p tau is designed to act as a delta function. So it is designed to have the property that if you act, it's designed to have the property that, if you act with, and the reason this comes about is because you can evaluate the inner product between psi t and psi tft, where this is the time shifted state and this is the thermofield double state. And you will find that that inner product, at least for small times, has the property that it looks like this. Okay. As a result of this inner product, this p tau has the property that it acts like a delta function. Okay. So what that means is that, if you act on, it's not actually, p tau has some width. So if you look at this p tau, you see that if you take p tau and you act on it on psi tfd, and if tau is very large, then you see that it basically gives you 0. It doesn't exactly give you 0 because you still have some exponential tail here, but it almost gives you 0 because this is some large extensive quantity that is proportional to n squared. On the other hand, if you take this p tau and you act on it, if you take tau equal to 0 here, then you get something that's 1. And so this p tau is designed with this measure factor, with this correct measure factor, to act like a delta function. So what happens as a result is that if you were to act on this operator on a state psi t, then this p tau picks out this e to the I omega t. The other parts of a omega L, the other parts of the integral just drop out, because you see the only part that gets picked out is a part where tau is the same as t, and that's because of this inner product. And so this becomes a omega L into e to the I omega t into ai into psi t. So this is the key equation. Okay. And the reason this equation works is because even though on top we have an integral over p tau, the most terms of that integral, or most of that integral, doesn't contribute because of this exponentially decaying term. But that integral for tau very close to t does contribute. And that is why you pick up this factor of e to the I omega t, and then you pick up a omega L. So you pick up this a omega L e to the I omega t. Okay? And that's why you need this measure, and that's why the measure is designed that way. And so now you find that this factor of e to the I omega t is precisely what you need to cancel off the troubling phase that we were getting previously. Remember, here we were getting a phase of e to the minus I omega t. And now, if we had a way, and as we have now, to take this a omega L and multiply it with e to the I omega t whenever it is inserted in the state psi t, as we have done here, then this e to the I omega t precisely cancels things off. And so once again, you find that a omega tilde a omega in any state psi t is indeed e to the minus beta omega over 2 by 1 minus e to the minus beta omega, which is not the correlator that a omega L has, but it is the correlator that a omega L into e to the I omega t has. Okay? So a omega tilde defined in this way does have the correct correlators, not only about the thermofield double state, but also about these time shifted thermofield double states. Okay? I hope that was clear. If there was something I missed or I was not clear about, please stop and I'll answer.
What is this theta cut?
Yeah, I'm coming to theta cut in a minute. 1 second. Yeah.
Can I ask a question about
Sure.
this?
Yeah.
So the a omega tilde like these are supposed to be state-dependent operators.
Yes.
It's not clear to me why it is, since we are integrating over time.
Yeah, I'm answering that as well. Yeah. Both these questions are related. The question about theta cut and this one is related.
I have a question. So can I simply say it here? You can for a time translated TFT state, you can consider A tilde as state dependent operators, where the state dependence is simply given by the space.
Exactly. It is only given by the space. That's right.
So like
but you need,
just take,
the point
so
is,
why do I need to define it like this in this projector language rather than just simply saying it's the left operator with the face?
You could say that. You could say that. Give me a minute. Okay. So you're anticipating some of what I'm going to say. Yeah. Give me a minute. Yeah. You could say that. You could just say it's a state dependent operator which just has this face, right? So why do I define it in this projector language? So there are 3 questions which were asked, which were all related. So why is this state dependent? State dependent. And why theta cut? Okay, so let me answer both. You see, why is this state dependent? In fact, it's state dependent precisely because of theta cut. Okay. You see, this operator does not work. Let me copy this operator. This operator, as I have written it, works for psi t, provided t is in the range minus theta cut is smaller than t is smaller than theta cut. Okay. Clearly, beyond that range, it doesn't work, right? If I take psi, if I act on it on theta cut plus 1, then it just gives me 0 because all the projectors are annihilating the state. So if I act on this operator, on psi of t, which is larger than theta cut or smaller than minus theta cut, I get 0. And so this operator acts correctly only for a range of states and not for all states. So you might say, well, very good. Here I'll improve the operator. Let me make it minus infinity to infinity. And now it will act correctly on all states. And what is more, by writing it this way, I have got a state independent operator because I've got an operator that works correctly for all states. But of course, this is wrong. Why is this wrong? This is wrong because remember, I told you the inner product, which was this inner product. But in fact, this inner product is not correct once t becomes large enough. In fact, you can check that if you just take the original thermofield double state and you evaluate this projector, then eventually this becomes of order e to the minus s for tau large. So this inner product is correct for small tau. It is not correct for large tau. And for large tau, this inner product just saturates and it develops a fat tail. So you see, if you had the inner product, which was this one, and it just kept going for all t, then it would tell you that, you take large tau and it becomes much smaller than e to the minus s, because remember, this is also n squared. So it just, you get some minus t square, you take t to be large, and you might get minus n cubed or something. So you might get some inner product that's much smaller than e to the minus s. But in fact, you see that the inner product develops a fat tail, and you can estimate, just using some random phase approximation, that this projector p tau acting on even the original thermofield double state for large tau just saturates to be order e to the minus s. So now let's take this ambitious operator that we had where the cutoff was minus infinity to infinity, and let's act on it on the thermofield double state. But now we find a problem, where this is the ambitious operator. Now we find a problem because look at the form of the integral that you're getting. You're getting some integral which looks like p tau on psi tft. And there are various phases, whatever, there's some e to the I omega tau, a omega L. But this integral is going from minus infinity to infinity. Okay, so that's the form of the integral you're getting. The other terms in the correlator, but let's just focus on the integral. But notice that this integral receives a contribution of e to the minus s for large tau, but it just receives a constant contribution of e to the minus s for all tau beyond a certain amount. Maybe eventually once you go to Poincaré recurrence time, that starts changing again. But for most of tau, it's receiving a contribution of e to the minus s. So this integral, in fact, is divergent. It is not a well-defined integral. And you see here that as a result, if you take theta cut to infinity, then this a omega tilde stops working even about the original thermofield double state.
No, the divergence couldn't be fixed by some I epsilon or something?
No, it's a physical divergence. It's not an I epsilon thing. It's the fact that you really have a fat tail that's coming out. You don't have to take this to be infinity. If you take this to be much larger than I'll say this in a minute. If you take this to be much larger than e to the s, then you will find that you will start, you'll start getting interference. This is the reason, as I explained, that state dependence really came about. You can always construct operators about different states, and then you can start adding together these these operators which you constructed about different states. And you might have thought, I'll add everything together and I'll get a state independent operator. That's the reason I wrote it as a projector. You might have said about the state psi t, I have e to the I omega t into a omega L. About some other state, I have a different e to the I omega t. Let me just add together all of these operators with projectors, which is how we discussed state dependence earlier also. And I'll get some operator that works in the full Hilbert space. But here, if you start doing that, because these operators far away, don't have an inner product that vanishes as you increase the distance in some sense of, in this one parameter state, you find that the operators far away start interfering, and that's what prevents you from getting a state independent operator. So this really is a physical obstruction, and it's telling you why state dependence arises. It arises because of this fat tail, and here you see it very clearly. In the earlier argument I made where I drew these Hilbert spaces and I said, well, they start colliding and so on, it was a very rough argument. In the eternal black hole, you really have a one parameter family of states, and you can very clearly and neatly see how this fat tail in the inner product of far away shifted states stops you from writing down a state independent operator. So the picture that you have is the following. Okay, here you have the thermofield double state. This is t equal to 0. This is psi tft. And you can write down some operator that works for a large range. In fact, you can even make this range exponentially large. So you can write down some operator that works, let's call this a omega tilde, which works. But once you go far enough from the thermofield double state, you need to switch to a different operator, which is now my operator marked in green. And you need to shift to an a omega tilde prime, which is a different operator from the original a omega tilde. And so you can take one operator and make it work for a large range of time shifted states. It's not that you have to use one operator separately for each time shifted state. You can use one operator for a large range of time shifted states, but for large enough times, you then need to switch. Okay? So that's the summary of the discussion. The summary of the discussion is that one operator works for can work for a large range of t, but not all t. And here you see why state dependence is necessary. Okay, so that is right. So that's that. Yeah. So I think that is what I wanted to say about state dependence and the resolution of these paradoxes. As I said, I think, if you want to think about state dependence, the eternal black hole example is the best example to think about, because you can see where state dependence originates. What is the problem that's forcing it to come about? It's this fat tail in the inner product. How you can write down something that almost looks like it's state independent, but if you get ambitious and you try and make it totally state independent, you'll find an operator that doesn't work at all in any state. And in fact, the paradoxes told you that you should not be able to find such an operator, because earlier we did find a paradox when we tried to construct such an operator. And so you expect that, something like this shouldn't work. And indeed, so it's not surprising that something breaks down when you try and construct a state independent operator, but here you can see exactly what breaks down. Okay.
I have a question.
Yeah.
So when I make this approximation of the state dependent operator with the left operators, one of the initial things we mentioned about how the left and right operators were different was by the Wilson line dressing you need to put on them to define them, right? So
right.
Is there a way to see how does that happen in this algebraic language?
Yeah, this is kind of the Wilson line dressing. You see, this operator A tilde omega has the property that H right on A tilde omega, well, within correlators, gives you omega A tilde omega. Whereas, of course, H right on A omega L would have given you 0. So, you needed this property to get the right phase. And indeed, once you add this projector and you add this factor, you can think of it as dressing it in the correct way, so that you fix the commutator with the right Hamiltonian, and you've made the commutator with the left Hamiltonian 0. So that's what this whole dressing does. It kind of flips the commutator from having a non-zero commutator with the left Hamiltonian to having a commutator with the right Hamiltonian. So that's what this procedure is kind of doing.
So is there?
But of course, you can't make it happen forever, right?
Is there a more geometrical interpretation for the dressing then? Right?
Of this projector, I don't know, and there might be, there should be, but I don't know of any more geometrical way of explaining why you should add this kind of term precisely to flip the faces. I mean, you can see that it works, but it would be nice to derive it in a more geometrical way. I don't know what the answer to that is. Okay, so I want to spend the second half of the lecture discussing something slightly different. Which is, I said a lot of good things about state dependence, and I said, look, it resolves all of these paradoxes, and you can see how, it helps you also in the eternal black hole. But, we need to be careful because we are doing something unusual. I gave you some physical arguments. I said, well, it's a cosmological context, so the question is unusual. And, maybe it makes sense that, you should ask about you should use state dependent operators, but we do need to be careful. And so I want to describe this question of the consistency of state dependent maps. Okay? So the question I'm going to, the problem I'm going to describe now was first described by Marolf and Polchinski in archive 1506.01337. It's called Violations of the Born Rule in State Dependent Horizons. The treatment I'm going to give you is actually going to use something which is a slight refinement of the same issue, which is described in this, which is the paper called Smooth Causal Patches, but really the puzzle was pointed out in this paper first. Okay, so I want to explain also that there's a lot of discussion about there's a lot of about state dependence, and people have various opinions, and somebody might say it violates quantum mechanics, and somebody else in the literature you might find saying that it's obvious and it just has to be the case, and sometimes it's used without comment. But really, I think that the question of the consistency of state-dependent maps reduces to the puzzle that I'm going to describe now. And this puzzle, in fact, has, I think, not received as much attention as it should. So I'm going to describe now a puzzle, and I'm going to describe a partial resolution to the puzzle. And I'll also, if I have time, describe some open questions. And I think this issue is really interesting, and it goes to the heart of some questions that we need to ask in ADS-CFT and about quantum gravity. And for some reason, it has not been, I think, discussed, or is not as widely understood as it should be. So I'm now going to describe a puzzle that appears with state-dependent maps. And the puzzle is the following. Okay? So it turns out that if A is state independent, then it must obey some statistical constraints. And the statistical constraints are the following. Okay? If you take a typical state and A has some expectation value in a typical state, and you compare the expectation value with the same typical state excited with a low energy unitary, where this is a low energy unitary. So let's look at the difference of the expectation value of A in some state, in some typical state at an energy, which may be the energy of a black hole, and the difference, how much you can excite A by acting on the state with a low energy unitary, right? So it's a pretty physical question. You have some microstate, maybe I have a glass of water here, and I act on it with some low energy unitary. So I perturb it very gently, and if I perturb it very gently, I can ask then, how much does the expectation value of some observable change when I have perturbed this state with some low energy unitary? Okay. So it turns out that if A is a state independent operator, then there is a constraint, and the constraint is that the change in delta A is given by, so this delta A, which is precisely what I wrote previously, psi A psi. This is bounded by twice of beta delta E sigma, where sigma squared is psi into A dagger A psi minus psi A psi squared. I'm assuming here that A is Hermitian, A is an observable, phi is not Hermitian. There's a simple generalization. And this is in the limit where beta delta E is much smaller than 1, and where this delta E is just the energy of the unitary. So it's how much the change in the expectation value of the Hamiltonian is. Okay? So you can define delta E as so let me just, I'll sketch the derivation here, but the punchline here is that, if you make an excitation, if you add energy which is much smaller than the temperature, so this is delta E divided by the temperature. If you add to the system an amount of energy which is much smaller than the temperature, then you cannot create an effective or an observable excitation. So this sigma here is just the fluctuation of A in the system. So that's setting some scale. And you see that if delta E is much smaller than T, then the statement is that there's a general statistical inequality which tells you that the change in the expectation value of any observable is very small. It's strictly limited. Okay? So low energy excitations cannot have observable effects where low energy is defined as an energy much smaller than the temperature of the system. So this is a general statistical constraint that one can derive, and I will now sketch for you how the constraint is derived and why it holds for state independent operators. Okay? So you see, what is this unitary doing? Right? What this unitary is doing is it's taking the Hilbert space at some energy E, and it's mapping it into some slightly larger Hilbert space at an energy E plus delta E. So I've exaggerated. The Hilbert space is only very slightly larger, but they're both very high dimensional spaces. But what you see, what this unitary does is it maps you from something here into an image of this HE inside this other space. Okay. So the unitary is maps you to this is some image of HE, which is embedded inside this bigger Hilbert space. Okay, so that is what the unitary does. Okay, but now let's call this space H of UE, which is just the image of HE under the unitary map. Okay, so that's what the unitary is doing. Now the unitary in the number on the volume of this H of UE in terms of the Haar measure on H of E plus delta E is very small. In fact, it's some high codimension space. So the volume in terms of the Haar measure, it's some high codimension space. So if you were to pick a random state in H of E plus delta E, the chance that you would really pick a state exactly in H of UE is effectively 0. But on the other hand, it is true that the dimension of H of UE is almost the same as the dimension of H of E plus delta E. So in particular, notice that the dimension of HE is e to the s, okay? And the dimension of H of E plus delta E is just e to the s plus beta delta E. Okay? So that's just the fact that del S by del E is beta. And so, if you change the energy by E plus delta E, you just get e to the S plus beta delta E, which of course is e to the S into 1 plus beta delta E. So the ratio of dimensions is very close to 1. So what does this mean? What this means is that let psi prime be a typical state in H of E plus delta E. Then you find that psi prime is writable you expect it to be writable in this form. Where the psi of this state is from HUE, and this is orthogonal to HUE. I hope this equation is clear. The reason you get this 1 minus beta delta E by 2 and the square root of beta delta E is just coming from dimension counting. It's the fact that if you take in a big Hilbert space, you just take some vector and you ask what's the projection onto some subspace. The size of the projection is just given by you can just compute that by the dimension of the respective subspaces. And so just by computing the dimension, you see that, if you take some vector and you project it onto H of UE and the space that is orthogonal to H of UE, you expect to find, this is some normalized vector, this is some normalized vector, and here I've put in the length, which is 1 minus beta delta E and square root of beta delta E. Okay. Okay, very good. So this so far is just kinematic, and it's just a decomposition of a typical state in H of E plus delta E. Let me now point out that the temperature, so let me now say a few things. The first is that the temperature associated with E plus delta E is also beta. Why is it also beta? That I said the entropy changes by beta delta E, but the temperature in fact doesn't change at all. And that's because you can compute the change in the temperature, and it's given by this. But notice that this is just divided by the specific heat, but this term is something macroscopic in ADS-CFT. This is proportional to n squared. This is something that's order 1. This is something that's order 1, or beta delta E is in fact much smaller than 1. Here you have something which is order n squared. This is the same specific heat. And so you see that the change, this is actually the change in the inverse temperature, but the change in the inverse temperature is very, very small. Okay, so it's basically zero. It's zero because you've divided it by some quantity which is macroscopic, and here you have some intensive quantities. Okay? And beta delta E is small because the total energy that you inserted is small compared to the temperature. Okay? So beta delta E is something that's, you know, some constant smaller than 1, and then you have beta divided by C, and that's clearly negligible in the approximation in which we're working. Okay? So maybe I can write order 1 over S, but effectively it's 0 for our purposes. So I see there's a question in the chat. Does having a fixed beta mean that the system is in the canonical ensemble? No, the system is in the microcanonical ensemble. So when I talk about the temperature associated with an energy, I mean that, you know, the system is in the microcanonical ensemble, but with the microcanonical ensemble, there is a corresponding canonical ensemble, which is, you know, what is the temperature at which correlators behave the same as, you know, as they do in this microcanonical ensemble. And what I'm saying here is, so, you know, I use the energy and the temperature in this sense when I talk about the temperature associated with a given energy. And all I'm saying here is that the temperature associated with the higher energy is also the same temperature as is associated with the lower energy. So, you know, the temperature changes only when you make a big jump in the energy. So the temperature, if you change the temperature by an order 1 amount, the energy changes by a large amount in the microcanonical ensemble. I hope that answers the question. Okay, so for this reason, you know, if you ask for the expectation value in the state psi prime, this is the same as the expectation value in the state, in some state psi, where this comes from HE. Okay. On the other hand, you know, here we had, you need to keep track of the notation. Psi E was the vector that was coming from H of UE. Okay. So you see that, in fact, let me copy this. So you see this. On the other hand, you see that psi E A psi. This is the expectation value of the operator A in some state which has been excited by the unitary, right? Because psi E is a vector which is the unitary acting on a vector in HE. So this is in fact psi of U dagger A U psi, where this is some typical state. So this is typical, everything, all the equations I'm writing here are true for typical states. So if you look at this equation and you compute the expectation value of A in the state psi prime, you see the expectation value of A in the state psi prime, in fact, is almost the same as the expectation value of A in the state psi. Here you have the expectation value of A in an excited state, and then you have some term of the order which comes from the cross term of psi E and A and psi O. And so you already see, just from this decomposition and the equations that are on the board, that psi A psi minus psi of U dagger A U psi is of the order of square root beta delta E. I previously wrote down a precise inequality where I put in some fluctuation or some standard deviation of the operator A. For that, you have to work a little bit harder. But even from the equation that's written on the board, you can just see that, you know, you evaluate the expectation value of A on both sides. Here you get the expectation value of A at temperature beta. Here you get the expectation value in an excited state. And then you'll get some cross terms, and the cross terms will be square root of beta delta E. And so just from here, you see that, you know, the change in the expectation value of A is of the order of beta delta E. Okay? And as I said, this is derived in, if you want to see more details, in archive, in the second reference I gave. So this is just some general property of statistical systems about the sensitivity to low energy excitations. Okay, so now why is this relevant for all we are saying? You know, why are we suddenly taking some detour and asking questions about low energy excitations? So the idea of this puzzle that was set forth for state dependent operators is the following. Let's consider the Schwarzschild number operator, which is n omega, which is this operator, which is our friend, and we have met it many times before. Okay. Now this operator has the property that it almost commutes with H. Why doesn't it exactly commute with H? It doesn't exactly commute with H because remember when we defined these modes, we smeared them a little bit. Okay, so they're not, they're not exactly delta function modes. They are slightly smeared modes for everything we've been saying so far. We've been neglecting the smearing, but okay, it doesn't exactly commute with S. We grant the fact that it almost commutes with S, and this is due to the smearing in A omega. So it's an operator that has almost zero energy. Let me take the unitary in question to be e to the I theta n omega. Okay. And then let me take the correlator, which is A omega tilde, A omega psi, which I have been considering several times. And let me take the operator under consideration A to be this product. Let me take it to be A omega tilde into A omega. Then you see that psi into U dagger, A omega tilde, A omega U psi gives you, if you compute, you see, because the number operator does not commute with A omega, but it does commute with A omega tilde by design. So you will see that you will get a factor of e to the minus theta into e to the minus beta omega by 2 into 1 minus beta omega. And this result is clearly in contradiction with the inequality I derived previously, because you see that the correlator has been modified at order 1. At order 1, the amount of modification depends only on theta. It does not depend on, this small delta E. I said almost commutes. So there's some small delta E that depends on the smearing. And this modification doesn't care about that small delta E at all. It just gets modified at order 1. And you see here that we have an example of a correlator that has been modified at order 1, which is in contradiction with the results that we derived. You can check that this contradiction would never arise if you didn't have a mirror operator. If you had put in A omega dagger here, then A omega dagger and A omega would both have, given you opposite commutators with U, and you would not have got this e to the minus I theta factor at all. So this factor arises only because you've put in this funny mirror operator, and that is what is leading to this problem. And you can check, it's not obvious, but you can check that for any operator, any state independent operator, you would never get this kind of a large modification with this kind of an operator. Okay? So this is maybe somewhat unusual statistical property, but it is a statistical property which is true, and you can check. And so you might say the paradox is that it looks like black holes are unusually sensitive to low energy excitations. Okay? So state dependence seems to suggest that black holes are very sensitive to low energy excitations. And that's a puzzle, because it's telling you that, black holes have some very unusual, that you use some unusual operators. And I was saying so far, and we discussed that, we use some unusual operators, but, you can't see the fact that they're unusual. The whole point of the state dependent construction was to say that, there's nothing, you can't see the fact that this is unusual because you can't compare these different states. And you have an observer who falls into one state. And so, you can't really compare. But here we are saying that, you have an observer. And if this observer, can create some excitation or can fall into a typical black hole and can try and excite the black hole, and we'll see that the black hole is anomalously sensitive to this low energy excitation. And that would tell the observer that something unusual is going on with the black hole. Okay? So this is an example of something that looks like, at least, would lead to trouble with state dependence. Okay? So now I'm going to explain in the last 20 minutes resolution, or let me call it a partial resolution. And the resolution, I think it's a partial resolution, but it's interesting. I think it's telling us something that's interesting. And there's some questions which are not answered, and I'll describe those as well. Okay? So far, we have been using the fact that, so is the paradox clear actually? Is there any question about the paradox or about the puzzle before I go to the resolution? Okay, so I'll assume the paradox is clear. So let me now try and describe the resolution. So far, we've been using this notion of simple operators, where we have said that, we've said simple operators are polynomials in the modes with some cutoffs, right? Are low order polynomials in modes. Okay, fine. But in fact, physically, one can do something. One can put some more restrictions on what are the possible simple operators and what are the possible perturbations that one can create for typical states. So let me discuss in a little more physical language, what are the possible perturbations that one can create for physical states. Let me first say something about perturbations. So everything I'm saying here is about possible simple perturbations and simple observations. So the paradox is the resolution is going to lie in a refinement of the notion of simple. So the resolution will be in a refinement of the notion of simple. And I'm going to refine both the kinds of perturbations that one can make and the kinds of observations that one can make. So let me first refine the possible set of simple perturbations. So you see, how do we act with a unitary? If I want to perturb a system, the usual way we perturb a system is we turn on some source. We can only turn on sources on the boundary. And usually what we say is we modify the Hamiltonian by turning on a source that is dual to some operator, which is Q. Okay? So this is an example of a simple perturbation where Q of t is a simple operator at time t. You see, simple is very important here, because if you allow me to use complicated operators, then all operators are at time t. Okay? If you allow me to use arbitrary operators, there is no distinction between an operator at time t and an operator at time t plus 100, because an operator at time t plus 100 can be written as e to the minus I into h into 100 into the operator at time 0 into e to the I into h into 100. And therefore, an operator at time t plus 100 can also be pulled down to an operator at time t. So it is only when you talk about simple operators that there is a sense in which you can say, here is an operator at time t and here is an operator at a different time. And that is because, if you talk in terms of, for instance, generalized free fields, there is a sense in which the generalized free field exists at time t. And that's not the same as the generalized free field at a later time. The generalized free field at a later time is some very complicated combination of generalized free fields at an earlier time. So in terms of simple operators, one can speak of operators being at a time t. So I emphasize that saying that an operator is at a time t relies on the assumption that the operator is a simple operator. Otherwise, there's no notion of the time of an operator. Okay, so if you take arbitrary operators, then the operator algebra is just a constant with time. Okay, let us say I act with this kind of a Hamiltonian. Then what do I find? Then I find that the state psi under this kind of deformation goes to the formula we study in QFT 101, which is it goes to a time ordered product. You just use the Dyson formula and the state gets modified to this kind of a state. And this is therefore the unitary U. So this generates for you a unitary excitation, but it generates a specific kind of unitary excitation for you. And I'm going to say that this is the set of physically or possible simple perturbations, where Q of t is a simple operator. I'm allowing you this set of perturbations, which is a physical requirement, but it restricts the set of unitaries that one can use. Okay, now let me ask about simple observations. So far, we have said that simple observations are observations of polynomials in the modes. But not all polynomials in modes are observable. in modes are easily observable. Why is that? Let me give you an example. The example that's relevant here. Here is a black hole. Here is some point x1 at the boundary. And here is my horizon. Okay. And here is my point x1. And let me draw a line from x1 to the singularity. And then let me draw the line back. Okay. Now, I hope you can see the line. It's a little faint, but I think you can still, this red line is just like, is just a line I've drawn. It's just a null ray. Now let me consider some point here, which I call x2. So now if I just ask for polynomials in the modes, I have a field. I can expand the field phi in terms of creation annihilation operators at this point x1. I can expand it in terms of creation annihilation operators at the point x2. And I might say that, look, I will measure the correlator of phi of x1 and phi of x2. This is just a 2-point function in the modes. But from a physical point of view, see this correlator of x1 and x2 is not observable by any observer. And the reason it is not observable is because these points x1 and x2 are not in the same causal patch. Okay? And what that means is that if you have some observer who goes and measures x2, so here's one observer, here's another observer, these two observers cannot possibly meet and compare their observations and therefore measure these correlators, because before they meet, they both fall into the singularity. So this person travels at the speed of light, but can at most reach here. This person travels at the speed of light, but can at most reach here. And that's it. So they can't meet before they hit the singularity. Okay? So of course, this is assuming some notion of locality, and all this is in the context of QFT in curved spacetime. But you see that, you know, this observable, even though it's just a 2-point function in the modes, from another point of view, is not easily observable. So this tells you that maybe you need to refine the notion of simplicity. And I will refine it so as to say, so consider observables which are maybe phi x1 to phi xn, where x1 to xn are in the same causal patch. What does that mean? That means that, you know, we can send light rays or time-like geodesics from each of these points x1 to xn, and they can meet before they hit the singularity. So for instance, if I were to take this point x3, this is in the causal patch of x1. Okay, so there are many causal patches, right? There are an infinite number of causal patches in the geometry. So there is somebody who could have measured this correlator x2. That person is here. You know, if I look at x4, then this person, you know, can measure x2. So you see that x4 and x2 are in causal patch. x1 and x3 are in a causal patch, but x1 and x2 are not. Okay? So causal patch is always, you know, we can only talk about whether a set of points is in a given causal patch or not. Okay? There's an infinite set of causal patches in the geometry, and we can only talk about we can only talk about whether a set of points is in a causal patch or not. And I want to restrict to observations which are in the same causal patch, which from the point of view of modes, which is the language we've been using so far, is a pretty unnatural thing. But, you know, it's something, it's an additional physical refinement you might place on the set of observations that can be made. Then it turns out that, and I should emphasize once again that this entire discussion, you know, is not keeping track of all these subtle effects of the loss of locality in the presence of gravity, and so on. So the entire discussion is within the framework of local QFT. And that's okay because we are talking about simple observations. So, there are more delicate observations you could make, where the notion of a causal patch might stop making sense, as we have ourselves discussed many times. But for simple observations, this is something that we might adopt. Then it turns out that the following is true. Okay? So these points, by the way, x1, x2 are the same causal patch, and as I said, they could be outside or could be inside the horizon. It turns out the following is true. Let u equal to e to the I let A be any observable of this kind, where x1 to xn are in the causal patch of this point TC on the boundary. What that means is that, there is a way so that you send this, so TC is this point here, which is on the boundary, and all these points x1 to xn are in the causal patch. So if you draw a diagram, then you would find that here is some TC, here is the singularity, and all these points x1 to xn are here. So maybe x1 is here, x2 is here, x3 is here, and there's a horizon, and some of them could be outside the horizon and some of them could be inside the horizon, but they're all in the causal patch of this point TC. Then it turns out that we do have the statistical inequality obeyed. And this is just a remarkable property of ADS correlators that one can show, but that I don't know of any simple explanation for. So this is just a property of ADS correlators, which is just true. And I wish I had a simple way to explain why this property holds, but I don't. And the statement is that if you take this unitary to be of the kind that we discussed, where you make some excitation up to some point TC, and then you make and you take some observable which is of this kind, then it is indeed true that the statistical inequality that we described holds. So notice what this means is that if you make if you were to make a time dependent transformation of this kind, where you were to modify things by a source, then you see what you get here is this kind of transformation of state. And if you modify something by a source and consider the deformation of this kind of an observable, then you are automatically insensitive to the part of the source that is outside, that is to the future of all of these points. Okay? So if you look at the property of acting with a source is that if you act with a source, you automatically get this cutoff TC. The source doesn't actually have to stop at TC. The source can keep acting for later and later times, but effectively the effect of acting with a source, because of this time ordered product, as you can check easily, and this is something that is standard in perturbation theory, you turn on a source, you evaluate some correlator at some time t, and the part of the source that acts in the future does not modify this correlator at a time t. So what this result tells you is that if one makes perturbations by deforming the Hamiltonian, or by turning on sources and measures correlators in a causal patch, then the anomalous sensitivity of black holes of BH is not observable. Okay. So I've gone through this a little bit fast because in fact the technical details are quite complicated, but it is in fact true. The punchline that you need to remember, and I would welcome you to try and look at the technical details in more detail. But the punchline is simply the following: that if one makes perturbations by turning on sources, which is a physical restriction one might put on perturbations, and if one puts an additional restriction on observables, in that one says that it's not that we only want to measure simple correlators of modes, but rather we want to put this locality restriction also on what is observable, in that we want to demand that we are measuring correlators in a single causal patch. Then within this set of simple perturbations and this set of simple observations, one cannot see this anomalous sensitivity of black holes. Okay. Now, let me just point out before I conclude this lecture that this is not a completely satisfactory resolution to the paradox. In particular, it does not address the thing that we started with. Right? You know, the paradox that we started with looked at e to the I theta n omega. In fact, this operator that we have here cannot be generated by deforming the Hamiltonian by a simple source. And that is because if you ask what n omega is, you find there's some Green's function C number, but otherwise it is O of t e to the I omega t into O of t e to the minus I omega t, t prime, t prime. And so to act with n omega at time t, or to act with n omega at time 0, requires operators from the future. And you can see that because this operator is not an operator that is local in time. It is the product of modes, and the modes are defined by taking an operator, integrating over a long time range. I didn't put some cutoffs, but you could put some cutoffs here, integrating over a long time range, taking another operator, integrating this over a long time range, and then multiplying these two. And so this operator is not of the kind you would generate by acting with a simple source on the boundary, because it requires you at time 0 to act with operators from the future. Okay? So I hope this is clear. So this kind of an operator does not actually fall within the ambit of the operators that we call simple perturbations. Okay? So, you know, we have a resolution and we can say, well, you can't act with such operators. But on the other hand, this is slightly unsatisfactory. It is slightly unsatisfactory because, you know, one might ask, you know, from the point of effective field theory, the point of EFT, one often does examine operators like, you know, operators like e to the I theta and w. And why is one not allowed to, you know, why is one not allowed to consider such observations? So of course, one answer is, you know, well, you know, you can't really consider such observations because, you know, you can never really observe something like this directly. But, you know, someone might say, well, you know, but I could measure a lot of correlators, and even if I can't observe this directly, I could try and infer what this is. And there is no good answer to that. So, you know, if you were to use these kinds of operators, which are outside the refinement we've made of simple operators, then you would find that this black holes have this anomalous sensitivity to low energy excitations. And secondly, you know, we also often consider correlators outside a causal patch. In fact, a very simple example of this is in the eternal black hole. In the eternal black hole, you know, you could take some correlator here, x1, take some correlator here, x2. These correlators are typically beyond the causal path. So, you know, here we have the eternal black hole, here's the horizon of the eternal black hole. And if you take some operators x1 and x2, which are, you know, not quite at t equal to 0, and you push them a little bit into the future, then you will find that these are outside a causal patch. But we often do consider, this kind of correlator in the thermofield double state, even though no single or no set of observers can measure this kind of correlator. We do often consider such correlators in effective field theory. And so the question is, why are we not allowed to consider such correlators in for black holes? Okay. So why do we exclude such correlators from simple observations? So we'll discuss this a little bit more tomorrow, but let me just summarize what the paradox was. Paradox is that we find that black holes seem to have an anomalously large sensitivity to low energy excitations. And the partial resolution is that if one puts a strict refinement, or one puts a strict condition on what is observable, and one puts in constraints from bulk locality, in that one says that the only kinds of perturbations one can make are turning on sources at a given time, and the only kinds of observations one can make are observations in a causal patch, then we find that this anomalous sensitivity is not observable. But on the other hand, it's a little unsatisfactory, because this, the earlier condition that we had, where we just said you look at polynomials in modes, that was a simple kind of condition that you could have said effective field theory is restricted to. But now we are putting some sharper condition, and one might worry about whether this condition is sufficient to put. Why is it that these kinds of observables, which we usually consider in effective field theory, one now wants to rule out from the set of simple observations? So we'll discuss this a little bit more tomorrow, but this is roughly the status of where this puzzle is. There's a partial resolution and there's a paradox. And as I said, I think this puzzle is really key to understanding this issue of state dependence. So we are out of time, so let me stop here and we'll continue tomorrow, and I can take questions if there are some.
Can I ask a question?
Yes, sure, yeah.
So isn't it normal that correlators like the ones that you consider at the end, so with one point in the left and one point in the right, from a book of view, seems quite natural that they are not simple correlators, in the sense that in order to compute those correlators, you should invoke some, I don't know, holographic property of the information where all the information is encoded on the boundary, but that will require some complicated operator in order to reconstruct the correlations between the 2 points in the two sides of the black hole, right? So isn't it natural that it's a complicated observable from a book point of view?
Well, it depends on in what sense. So we don't need to use some holography of information here. I'm just thinking of a 2-point correlator field. So if I were to expand like the field on the right, like in terms of modes on the right, like I write it as OR omega e to the minus I omega t plus HC. And I write the field on the left in terms of modes on the left. Then I will get some value for this. I'll get some value for this, which will just be like some sum of OL omega, OR omega with some factors. So I'll get some 2-point function, which is just really a 2-point function in the elementary modes. So here let's just do quantum field theory in curved spacetime. Let's just forget about gravity. So if we just do quantum field theory in curved spacetime and we don't even have gravity, this is just a 2-point function of the modes. But it is true that no observer can measure it because of the way the geometry works. By the time an observer measures this, and if they try and communicate the results, they'll fall into the singularity. So this is something which is mathematically well defined in effective field theory. We compute such some things, things in QFT in curved spacetime. But it's true that observers can't really measure them. So that's why from one point of view, it seems that this is a correlator which is unobservable. But on the other point of view, it seems that it's also an observable which is natural in effective field theory, and maybe observers making observations in different causal patches could somehow infer what the value of this correlator would be, even if they can't observe it directly. So here we are having to exclude such correlators if we want to say that black holes are not anomalously sensitive. So they are not by themselves complicated, and even in QFT and curved spacetime, such correlators are measured or are defined and calculated, although they're not directly observable. Did that answer the question? Or?
Yeah, the only thing I mean is, like, from a Boole point of view, it's in some sense a unnatural correlator to compute.
Right.
So you still have to invoke some property of the boundary theory in order to understand that as a simple correlator. So understand why you have to invoke the fact that you have an operator on the boundary, and from the point of view of boundary operator, that's a simple operator that you can just compute because you have control over the two CFTs. But from a Boole point of view, you are still considering a correlator of between fields in 2 points that are causally disconnected. Like it seems quite natural that cannot be included as a bulk observation, which is simple, right?
Yeah, okay, I agree with you. I mean, from that, I mean, we could also say this about observations which are here. Like if you make an observation here, like one here and one here, like these two observations are also disconnected. And so you could say that but bulk effective field theory will give you some answer to this correlator. It'll tell you there's some geodesic length or something. But you're right that, from another point of view, it's an unnatural observable. So maybe that's the answer. Maybe you could say that, you just refine the notion of simple observables in the way we described, and you reformulate things in that way. Of course, this mirror operator construction and so on wasn't quite done with this language. It was done with this modes thing. So you'd have to rework things, but maybe this is the answer. And maybe one thing I should have emphasized or didn't emphasize more was, it is kind of remarkable that this answer comes about. Like, it's as I said, I don't know of any simple way to prove this, to motivate this result. It just so happens that there's some remarkable property of ADS correlators that makes this answer true. And so maybe this is telling us something, and maybe this is telling us that we should refine the notion of simplicity. But it's different from the notion of simplicity we were using before, which was just low order polynomials in the modes. And maybe this is telling us that this is what we should do. So that's a possibility. I agree.
Thank you.
I mean, I have to say, at least personally, I'm a little uncomfortable with it because I have always been uncomfortable with this notion of causal patches. I've been uncomfortable with this notion that you have you restrict to things in a causal patch, and it would be nice to have something that describes things even outside the causal patch. But maybe that's an unreasonable bias that I have, because as you say, no bulk observer can really measure something outside a single causal patch, and so why should the theory give you predictions for that? And so maybe this is just teaching us that that's how we should think of things.
Yeah, I understand what you say, and I agree that it'd be nice to have a global, let's say, picture. But that global picture, I think, isn't that like strictly related to our idea that we have a dual theory, because in one sense, like if you are a bulk observer and you believe in locality, then it doesn't really make sense to talk about anything which is outside your causal patch, right?
Yeah, I agree. Yeah. I mean, of course, one would have to be careful about what happens if one includes the effects of gravity, and then then one would have to be more careful because you would have these effects also at space-like separation, and so that's one difficulty of working with causal patches, and that this is good at the level of local QFT, but then one would have to be careful about how to build that up into a complete theory when one starts including 1/n correction. So that's one thing. But you're right. I mean, maybe
if you have no local gravitational effect at that point, sure, you have to consider also global properties. Yeah.
Right, exactly.
Okay.
But those are 1/n suppressed effects. So maybe this answer is already good enough at order 1. But yeah. So there's another question.
Thank you.
So I thought somebody else had another question, which I interrupted.
I don't think it was me who had this question because I was muted. So if it's someone else, I'll wait. Otherwise, I have a question.
Sure, go ahead.
Okay, I will ask. So can you expand a little bit on this, on how we can infer this correlator, the last one, from correlators within one causal patch?
Well, I mean, it would roughly be the fact that if you made a lot of observations within a causal patch, you would kind of detect the bulk. You would know the bulk Hamiltonian and the bulk interaction terms, and therefore you would be able to determine what was happening. If you could. So you could make some observations first in this causal patch, and then you would know some bulk Hamiltonian here, and then you'd need to combine a lot of observers. So you're right that no single set of observers would be able to do it. But if you had access, yeah, I mean, you're right that no single set of observers would be able to do it if that was a question. But you're right. The idea was, let's say you had lots of observers and you could ask them to make observations first in this causal patch and then this one and then this one. Then they would like measure correlators, and using that they could reconstruct some effective field theory in the bulk, and they could use that to compute what this is. But as you say, that kind of requires a super observer who can combine these experiences from different causal patches, so it's not something that a single observer would be able to do. But maybe the more precise statement is the following. Let's say I told you the correlators within every causal patch, then that also probably fixes these correlators. So let's say I told you, yeah. So maybe here's say we are given. I don't have a proof, but I think this may be true. I think this should be true. Say we are given phi x1, phi x2, when x1, x2 are in a causal patch. And we are given all pairs, for all pairs. So this does not directly include the correlator I was discussing here, because this is not one of the set. But I think if you gave me this data, like you gave me data of phi x1, phi x2 for all pairs x1, x2, then I would be able to use that to reconstruct something about the fields. And so I would have data about some pair here, but I'd also have data about some pair here. And I think one might expect that maybe one could reconstruct therefore data about the bulk Hamiltonian, and therefore reconstruct these correlators which are outside. So that was the sense in which I was saying things, that if you were given like correlators for all pairs of points in all possible causal patches, for all pairs in all causal patches, then you might be able to also reconstruct correlators outside a causal patch. There's no proof, but I was thinking that might be plausible.
Okay, I understand, but this still involves using multiple causal patches. So
yes,
yeah, I understand what you mean. I understand.
Yeah,
thank you.
I agree. Yeah.
Oh, actually,
sorry.
Oh, sorry. Go ahead, please. I'll wait.
Okay. If I'm not mistaken, you mentioned that the title of the paper by Maroff and Polchinski was had violation of Born rule in it, but it is not clear to me how this sensitivity to small perturbations leads to violation of Born rule. Can you say a little bit on it?
Yeah, it's from here. You see, yeah, so if you it's from here. If you have this, you see you have this decomposition. So this is just a kinematical decomposition. And now I'm going to say, look, let me put in some observation here. And if it so happens that so let's say A was a projector, which is one example you could take. Then you see that you have some operator here and you have some operator here, where this operator is almost this vector is almost equal to this vector, and therefore you would expect that the expectation value of a projector in this vector is almost the same as an expectation value of a projector in this vector, because these two vectors are almost parallel. Of course, these vectors are very atypical. These psi e vectors are very atypical, but you can always find a vector that's almost parallel to any vector in the Hilbert space through this kind of a decomposition from psi e. And then there is this additional contribution which is of small length. And so if you were to take this A to be a projector, then you would expect that the value of the projector, if you have some physical feature of the geometry, like is there a firewall or not, which you would expect to be given by a projector, then the value of the projector in this state should be almost the same as the value of the projector in this state. And that directly leads to this, this condition that we have here. If it so happens that the value of the projector So let's say we go back to this example that we had previously, where psi e was e to the I theta nw acting on a typical state, then we would say the value of the projector for such states was 1, in that such states have some firewall because you've dephased the modes outside and inside. But on the other hand, typical states at a slightly higher energy do not have a firewall. So there must be two states that are almost parallel, one of which has a firewall and one doesn't, and almost parallel being given by this. They're not exactly parallel. And so it must be somehow that there are two states which have a large inner product which give you different physical answers.
I see. Thank you.
So my question was, I'm not sure it's even a well-defined question really, but I will ask anyway. Is a discussion such as this one being carried out for asymptotically flat spacetimes? So for example, starting from the fact that mirror operators are state dependent, is this believed to be true in asymptotically flat spacetimes?
Yeah, that's a very interesting question. I was planning to say something about it tomorrow. In fact, it's not clear if you need state dependence in asymptotically flat spacetimes. And the reason is that the entire reason we were forced to state dependence was because black holes were dominating the canonical ensemble. And so we ended up, or dominating the microcanonical ensemble. And so we ended up with these paradoxes, which forced us into this. So we could say we have firewalls, or we could say we have state dependence. But in the case of black holes in asymptotically flat space, they never dominate the microcanonical ensemble. So a black hole state in asymptotically flat space is an exponentially atypical state. If you only want exponentially atypical states, if you only want mirror operators that work in exponentially atypical states, then you can come up with a state independent construction. So we don't know of any argument that tells us that in asymptotically flat space, the interior operators have to be state dependent. That doesn't mean there is no argument, but we just don't know of any. So we don't know of any reason that tells us that you have to have state dependence in asymptotically flat space because the kinematics is different. Similarly, for small black holes in ADS. So the state dependence is required if you want to describe typical states as having a smooth interior, but asymptotically flat space is different. So it is possible. One possible way out is you could say we don't like state dependence, so we'll just not use state dependence, and we'll agree that typical states in ADS CFT have firewalls, and there's something wrong with the eternal black hole which we need to fix. But all that would still not say anything about asymptotically flat space. It's still perfectly consistent with the idea that asymptotically flat black holes are just what we expect, and there's just something pathological about typical states in ADS CFT.
Thank you. Thank you.
Yeah, I have a naive question, I guess.
Sure,
so,
yeah.
So we have seen that delta A, where A is the state independent operator, is bounded under the action of low energy perturbations.
Right.
But is there any reason to believe that if A is state dependent also, then it should be bounded?
No.
Because otherwise.
No, it's not. Yeah. And indeed, that's the violation we are finding, right? So we are finding that if you take this operator A omega tilde, so the point is that state dependent operators might act differently on this and on the sum, right? Because they're not linear operators. So this is kind of trying to bring out the fact that they're nonlinear operators, and so they act differently on this and on the sum. And so that is indeed what we are finding. That if you look at the variation here, you got this factor of eta minus theta. But the point is that that's a problem, right? Because now you're saying that, the words we had for state dependence were to say, look, they act linearly within the little Hilbert space, so there's nothing you can do to observe the fact that you have this violation. And now we are finding that, look, you act with this unitary, which is of this kind. And if you say this is an observable, this whole thing is an observable, then you will end up in trouble because you'll find a violation of this rule. And so that is the question of the violation of the bond rule. On the other hand, I mean, the resolution is that, you can't really act with this because this n omega involves operators from the future. So it's not like a local operator at a given time. And so it's, you can't, so the resolution is that you need to refine the notion of observable. And if you refine it, then you will not be able to observe this phase. But if you could observe such a phase, then it would tell you that there was really something unusual about the black hole interior, right? And then you would question why you should use state dependence. And you might say, well, maybe I'll just agree to the fact that black holes have firewalls.
Okay.
So
yeah.
so the short answer is state dependent operators do not need to obey this inequality as they do.
And only the interior operator is an example of state dependent operators. I mean, are there any other examples like?
So in the exterior, you don't need to use state dependence.
Yeah.
And indeed, you could check that for the exterior operators, even though it's not obvious, you would never get such a paradox. As I said, you have, for instance, a correlator which is psi a omega dagger a omega. Psi is 1 by 1 minus e to the minus beta omega, and this would not pick up a phase under this kind of an excitation, because a omega dagger and a omega would pick up opposite phases.
Okay, yeah.
And any other questions?
Sorry. I just yeah. So if we take instead of a number operator of tildes, right? And in the equation
n omega tilde. Yeah.
Yeah. Then that has a theta. That doesn't have theta.
You would not have a problem still for this. It would just commute with everything. N omega tilde would just commute. You would still not have a problem.
Okay, yeah, fine.